Guys, welcome to lesson 7.2. We start looking at some matrices operations. So we're going to go through the very basics of matrices to begin with here, because good chance a lot of you have not been exposed to these before. So when you have a matrix like any of these, first of all, the things that go left and right are called the rows. If you look at it from top to bottom, we have a column. So if I look at 3, 6, that would be row 1. If I look at this guy, that would be row 2. If I look at it this way, this would be column 1, and this would be column 2. So the first thing that we're going to look at is how do you identify the dimensions of a matrix. The dimensions are always rows by columns, and so that's what I got right down here for you. I'm trying to get all this on the screen so you can see it. But we always name it by the number of rows, by the number of columns. So if you look at matrix A, you can see this is row 1 and row 2, so there's 2 rows, and column 1, column 2, so there are 2 columns. So this is a 2 by 2 matrix. If you go to matrix B, you can see that I have 2 rows going left and right. However, this way I have column 1, 2, and 3, so I have 3 columns. So it's a 2 by 3 matrix. Right here, you got 1, row 2, and row 3, so there's 3 rows. And from top to bottom, you have column 1 and column 2, so this is a 3 by 2 matrix. On this guy right here, which is kind of a special case, we'll talk to you in a minute. Obviously, another 2 by 2 column, or a 2 by 2 matrix, sorry. And then again another 2 by 2 right here. So just want to get used to how we identify the dimensions on these. What you're seeing on this that we'll be talking about a little bit later is called an identity matrix. An identity matrix is basically like a value of 1. You know that if you multiply a number times 1, you simply get that same number, right? That's what we call its identity. So way back even in Algebra 1, when you learned all your algebra properties, one of them was the multiplicative identity property. In other words, if I multiply something times 1, I get that same number. So if I were to multiply this times another matrix, I would get this matrix as my answer. So it's like a value of 1, so we call it the identity matrix. That's anytime you have 1s in the center downward diagonal and 0s everywhere else, right? And we'll talk about that a little bit more later. So let's talk about just one of our first basic operations here, which would be just to multiply the entire matrix by a scalar. So I'm going to take in a single number and multiply it times every value in matrix B. So when you see it written this way, we are simply taking all of matrix B. So I'll just write it out real quick. So I had 3, 1, 0 in the top row, 2, negative 4, 2 in the bottom row. So I'm going to multiply all of matrix B times a scalar of 3. It's just distribution. That's all that is. So I'm just going to multiply every value in there times 3. So that would become 9, that would be 3, that would be 0, 6, negative 12, and 6. And that would be it. So this would represent 3B. As far as adding and subtracting, something super key to this, in order for you to add or subtract 2 matrices, they must have the same dimensions. Must have the same dimensions. So, in other words, I can only add a 2 by 3 matrix with another 2 by 3 matrix. Right? If they're not exactly the same, then you cannot add or subtract them. I'm going to write these down real quick. So matrix A was 3, 6, negative 1, 2. And matrix E was 7, negative 5, 4, negative 2. So you can see on these guys that I am allowed to add them together because they are both 2 by 2 matrices. I'm allowed to do it. And it's real simple. All you do is add up their corresponding parts. So it's like if you were to take this one, pick it up and set it right down on top of this one, then you add those numbers that are on top of each other, right? So in other words, the top left, the guy that's in row 1, column 1, would add up with the other value in that same position. So my 3 goes with the 7. My 6 goes with the -5. -1 adds with the 4. And 2 adds with -2. My dimensions won't change. So if I add a 2 by 2 with another 2 by 2, my answer should also be a 2 by 2 matrix. So here's just a little more with the operations. So now we're involving, we can quite keep building on these operations, but we're throwing in a scalar, and then we're going to do subtraction. Guys, just like PEMDAS, you have to consider what needs done first, right? I need to multiply before I subtract. If I tried to subtract first and then bring in the scalar, it would not be correct. So I'm going to start by just multiplying matrix D, which was the identity matrix, times 3. And so if I did that, we're going to get this look right here. Now let me bring in matrix A again. All right, so I multiplied D times 3 and got this guy. Now I can subtract, and again, it's possible because they are both 2 by 2 matrices. So again, match up the corresponding parts. You can, I know you saw this as early back as probably pre-algebra, but whenever you're subtracting multiple items like this, you can, if you want, change this to a plus and then change all the signs behind it. And if that helps maybe guard you against issues with double negatives or things like that, you're always welcome to do that if it feels a little safer to you. But let's just subtract all the corresponding parts. So on the upper left, I have 3 minus 3. Upper right, I'm looking at 0 minus 6. Bottom left, and here's where you got to watch out for those double negatives. So technically, this is going to be 0 plus 1. And then in the bottom right, 0 minus 2. And there's our result. So just to show you, again, if I wanted to add A plus B, so take a look, could we add those together? Right? And obviously you can't because they do not have the same dimensions. So when you run into those cases, we just simply say it's not possible. Can't do it. All right. So here's an operation that's just a little trickier at first glance, but you guys will see that after you've done this a couple times, really not so bad. It's just a little bit of a process that you have to get used to initially. First things first, this is the one time where order matters, even in multiplication. Right? So typically in multiplication, you can switch the order of things, and it doesn't matter. Well, that's not true when it comes to matrices. Order matters in matrices. So in other words, if I were to multiply matrix A times matrix B, it would be different if I did B times A. So do not switch the order of your matrices. When you're asked to do something like E times B, you got to keep it that way. You cannot switch the order. You will get a different result. First things first, how do you know when you can or can't multiply matrices? So here's what we look at. So here's my first matrix. Remember, it's rows by columns. Here's my second matrix, rows by columns. In order for you to be able to add them together, this is what must be true. The columns of the first one must match the rows on the second one. Those numbers must be equal to each other. If they are, then you can multiply. So what will the result look like? The result will look like these numbers. So whatever the number is here will be the rows of your result, and whatever the number is here will be the number of columns in your result after you multiply. Okay, and so let's look at E times B. So I'm pulling these from the previous page. I already wrote them, so we don't have to flip back and forth. So if I wanted to multiply E times B, the way that we multiply, well, first of all, let's start with this. This is a 2 by 2. This guy is a 2 by 3. So first things first, yes, we can do it because those numbers are equal. What will our answer look like? look at the outer numbers, our answer will be a 2 by 3 matrix. So this result over here is going to be a 2 by 3 matrix. So here's how you multiply two matrices together. When you multiply, we always do a row times a column. Row times column. So I'm going to do a row times the first column. Then I'll do this same row times the second column. And then I'll do the same row times the third column. And that's going to give me my 3 top row answers. And then I'll jump down to the bottom row and do column 1, bottom row times column 2, bottom row times column 3, and that's going to give me my 3 answers on the bottom. And so that's where we're going to get this 2 by 3 matrix. What I'm showing you here is kind of the full process. I would not expect you guys to write this out for every one of these, but I wanted you to at least have it for your notes. So that if you ever need to look back on this, it'll be here for you. So I'm going to start by doing row 1 times column 1, and that would go right here. When we multiply the first numbers together. So 7 times 3. I multiply the second numbers together, -5 times 2. And then I add the results. So 21 plus -10 is going to be this guy. So let's go to the top middle. So if I did the top row times the middle column, again, first numbers together, 7 times 1. Second numbers together, -5 times -4. And then we're going to add the results. So this is going to be 7 plus 20. Let's do the top row times the far right column. So again, 7 times 0. Love those zeros. And then -5 times 2. And if we add the results, I should just get -10. Alright, so that takes care of the top row. We're going to do the exact same process now using the bottom row to get our bottom row answers. So if I did my bottom row times the first column, I'm looking at the first numbers together, which would be 4 times 3. The second numbers together, which would be -2 times 2. And then I want to add the results. So 12 plus -4 gives us that guy. Let's do 2 more of those real quick. So bottom row times the middle column. So first numbers together, 4 times 1. Second numbers, which would be -2, -4. Add the results, so 4 plus 8 would give you this guy. And then 1 more of these, so 4 times 0 plus -2 times 2 should add up to -4. And that is our answer matrix. So that is the multiplication process. Again, only possible when these numbers match, so you always want to check for that. So just to reinforce something I talked about just a minute ago, if I switch the order, would I get the same matrix? Is it even possible? So instead of doing E times B, if I switch the order and make it B times E, look what happens now. So the dimensions on, if I switch it to this way, I have a 2 by 3 with a 2 by 2, right? In this case, not even possible. So recognize those cases that are not possible and move on. Give you one to try on your own. If you want to try this one, you're welcome to pause and I'll follow right behind you. Here's the way I would do it to save myself some time. I don't write down every step like I just did on that previous one. You certainly can, but that's not expected of you. I think most of you guys probably do this stuff in your head. Obviously, if it's on a test or something and you want to be safe, feel free to write stuff down. So if I do a 2 by 2 with another 2 by 2, first of all, yes, it's possible. My answer will be a 2 by 2 matrix. So I'm going to do the first row times this column. So first numbers together, so 21, 24. If I add those together, I get 45. To the second column, negative 15 plus negative 12 will give me negative 27. Bottom left, negative 7 plus 8. And then 5 plus negative 4. So assuming I did all that right in my head, that's what it should look like. I guess one thing I would probably do if I really wanted to be safe about this is I could at least write down the numbers off to the side that I'm doing in my head. Like if I were to do, say, the first row times the first column, I might say 21 plus 24, and then make sure I'm safely adding those together to get the result. So you could always write down some side work, but again, I'm not expecting you guys to write out this for all of these. I just wanted you to at least have this for your notes. Moving on. So if you turn 2 pages over, you'll get to this page. So we're going to look at the idea of a determinant of a matrix. And there's really just a kind of a general understanding of a determinant is with the process that we use to find a determinant, it is sort of a process within a process. Really a determinant is used for other processes. So it's really just a step in other processes. If we want to solve an equation, find an inverse, there's all these things that we can do with a determinant, and there's really no great definition for what a determinant actually is, other than it's just a value that's used for other processes, like solving an equation. We do represent it with absolute value brackets. So when it comes to matrices, if you see the name of a matrix wrapped in absolute value brackets, that is their symbol for a determinant. So if they just said something like find this, and that's all they gave you, right, they're asking you to find a determinant of that. 2 by 2s, super easy. With a 2 by 2, all you have to do is the downward diagonal minus your upward diagonal. So in this case, with those letters, it would be AD minus CB. So downward minus upward. So real simple with a 2 by 2 matrix. By the way, these are only done on square matrices. So it could only be done with a 2 by 2, 3 by 3, 4 by 4. So it's got to be a square matrix in order for you to find the determinant of it. So if I did my downwards, which would be 3 times 2, minus my upward diagonal, which would be 2 times negative 4, so let's clean that up. We're looking at 6 plus 8, which is 14. So the determinant on this matrix would be 14. And again, that's just a value that we'll be using in further processes. So what I'm going to ask of you guys, because to be honest, everything that I've showed you so far can be done in a calculator, right? All of it. So there's going to be certain things I'm going to ask you to do by hand. There's going to be certain things that I'm going to allow you to do on a calculator. Just so, for one, I want to make sure that we understand a process, but also I want to make sure that you guys also get to take advantage of technology. So when it comes to a 2 by 2 matrix, I want to show you how to do this by hand. But realistically, when you start getting into larger matrices, like a 3 by 3, the process becomes so tedious that realistically, it's not something we would ever do by hand. We were going to use a graphing calculator for something like this. You know, when it comes to doing this by hand, honestly, I could do it by hand even faster than I could put this into a calculator because it's so simple. So there really is a need for an efficiency of doing some of these by hand when they're very short processes, right? There's no reason I need to put this into a calculator to get a determinant. So anyway, what we're looking at in this section now is finding the inverse of a matrix. Well, within the process of finding an inverse, you need the determinant. So that's why we learn how to find a determinant, because in getting an inverse, that's one of the things that you need within that process. So let me give you a quick overview of the full process here. So if I want the inverse of this, and again, guys, really the inverse is, again, another step in a further process of solving equations. So this is kind of like step 2, right? So understanding how to find a determinant is step 1. Finding an inverse is step 2. And then step 3 is going to be using that inverse to solve an equation. And so that's where all this is headed. So this is kind of like step 2 of the process, is getting an inverse. And you'll see why as we kind of keep moving forward here. But first things first, they say determine whether it has an inverse. Well, here's how you'll know. Here's what the inverse looks like. It's really not as bad as it looks. The first step in that process is to do 1 over the determinant. Well, obviously if your determinant is 0, then this is not possible because you can't have 0 on bottom of a fraction. So if you ever get 0 for your determinant, then it's not possible to find an inverse for that matrix. If it's not 0, then you can move forward with the process. Okay, so the first thing we would have to do on this is figure out the determinant. So we would do the downward diagonal minus the upward diagonal. So you would say -4 minus -6, which is obviously 2. So what they're going to do within this process is they're going to do 1 over the determinant. So that's what you're seeing right here, 1 over 2. And what they're going to do with that is they're going to multiply it times sort of an altered matrix. So here's what you're seeing right here. So here's how they get this altered matrix. What they do is they take these two values and they switch them. So they're going to take -1 and 4, and they're going to trade places with them. So here they are. The other thing that they do is they take these two values and they change their signs. So if you look at these two values right here, this is going to become -3, +2, and that's what you're seeing right here. So what they're going to do is they're going to take 1 over the determinant and distribute it to this altered matrix in order to get the inverse. And that's it. That's the process for getting an inverse. So what does it mean to have an inverse? Well, if I were to take a value, multiply it times its inverse, what do you always get? You get 1, right? So if I were to take a value, multiply it by its inverse, I get 1 as my result every time. So as far as matrices go, same deal. If I take the inverse and multiply it times the original matrix, I would get a value of 1, which is an identity matrix. So if I did this guy times this guy, the result would look like this. Oops. Which is the identity matrix. So it's like having a value of 1. So you could always do that to check your answer if you really wanted to, but that's the idea. And you'll see why that gets used later on to solve equations. So that's the process on doing it by hand. Now with the 2x2 matrix, that's very simple. Very simple to do that. However, when it comes to 3x3s or bigger, this process becomes very lengthy. And so that's not something I'm going to ask you to do by hand. Let me show you how you can do this on a graphing calculator. If you don't have a graphing calculator, I have no doubt that there are online tools aplenty that could handle matrices for you. So I'm sure you could easily search up some kind of matrix solver or something like that you could easily do the same process with technology online. So let me show you how it would go on here. Your matrices section is right here where it says matrix. It's in blue, so I got to hit second matrix and it pulls up my matrix stuff. So whenever you want to input a new matrix, go over to edit and hit enter. Right? This is what you're seeing was something that was just already in my calculator. because it never erases. It'll always save your last matrix that you created. So what we're going to do is we're going to put in matrix B. So the first thing you have to tell your calculator is what are the dimensions of matrix B. So this is a 3 by 3 matrix. So I'm just going to type over what was in there. So I'm putting in the dimensions of a 3 by 3 matrix, and I'm just going to type over what's already in here with the new numbers. So there's our new one. So now I've created this guy in my calculator under the title of matrix A. So, and it's going to stay there. So like I can hit quit and leave that matrix feature and it'll still be there, right? It's not going to change anything. It's forever in there until I change it. So here's a couple things you can do with that. One is we can find a determinant, right? That's what I showed you earlier on. If I wanted to. So watch, go back into matrix. Your operations are under this middle column that says math. And the first one in that list is determinant. So I'm just going to hit enter. And my calculator is saying, okay, what do you want me to find the determinant of? Well, I want it to find the determinant of the matrix I just put in there. So I need to go back into matrix. And the one I put in there was matrix A. So under names is where you can take the matrix that you created and put it onto your home screen. So I'm just going to hit enter. So it says determinant of matrix A. Hit enter. And there's my determinant. So real simple. You can do that with any matrix. And like we looked at is, as long as it's not 0, then I can continue with the process and get the inverse. Real simple to get the inverse. Again, I'm going to go back into matrix. I want to identify that it's matrix A, so I'm just going to hit enter. And now I can do whatever I want with this. I could multiply it by a scalar. I could multiply it to another matrix. Anything you want. You can do now with just any basic operation to that matrix. What we're doing is finding the inverse. So I'm going to raise that to the -1 power to get the inverse. So if I hit enter, there's the inverse. So that is now the inverse matrix of this guy right here. So if I were to multiply this times this, I would get the identity matrix, which looks like this. So that is the identity matrix of a 3 by 3 matrix. All right. Let's move on. So here's where things will end for us. Just a little practice if you'd like some extra practice. Again, one thing I wanted to point out on this one, guys, is if you tried to find the inverse of this one in your calculator the way that I just did, it's going to say does not exist because, or it's going to say error. It doesn't exist because the determinant of this is 0. And that's why it does not exist. So just a heads up on that. You can certainly run into those cases. So let's just start with, let me show you something with number 20 really quick. So again, if I were to even try to do this one by hand, remember it starts with 1 over the determinant. Right? So even if I try to carry on this process, I'm going to see that my determinant is 24 minus 24, which is 0. So here's a case where it doesn't exist. Right? So let's do one that does exist. So let me go to 19 here. So for 19, I'm going to do 1 over the determinant, which would be 6 minus 1. And I'm going to multiply that by that altered matrix where the 2 and the 3 trade places. And the upward diagonal changes signs. So those guys both become negative. So all I have to do is distribute that 1/5 times each of those numbers, and I'll have my identity. So up here I would have 3 over 5, negative 1 over 5, and that's it. So again, that's my inverse. So if I were to take my inverse, multiply it by the original matrix, I would get the identity matrix of a 2 by 2. All right, let's go down to the last one. Again, here's what we can do with some calculator usage. Just so you guys know, and I think it was under, let me check real quick. If you go under F3, that green F3, so I hit alpha F3, you might have a matrix menu on your home screen. And so I don't know if every calculator does this. It might depend on how current your TI device is. So you can always do it from here if you want. You just identify the rows and the columns, you put it into your home screen, and that's it. So since I already showed you how to do this in the matrix feature within the previous problem, let me show you how you could do it this way too, because some of you might have access to this menu, and you can do it this way. 24 is a 3 by 3, so I want to identify this as a 3 by 3. So alpha F3, let me get up to that one, there we go. So this is now a 3 by 3, I'm just going to hit enter. After I go back down to OK, I'll hit enter. So, whoa. Alright, let's try that one more time. Alpha F3, 3 by 3, hit enter, there we go. So now I just have to put in the numbers. Here's what you don't do. Don't hit enter. Right after each one, you have to like scroll through. So I'm just going to keep scrolling to the right after I put in each number. So 0, 2, 2, just keep scrolling to the right, and it'll take you through these guys. Okay, so now the matrix is here on my home screen. I can do whatever I want with it, right? So if I want the inverse, I'm just going to raise it to the -1 power and hit enter. And there's my inverse. If any of those numbers are rounded, you can always change them to fractions. Like if you need like exact values instead of decimals, like those look exact to me, so I don't think those are rounded, but you know, let's just say you had a rounded decimal. Well, you could always go under mode, oops, not mode, math, fraction, so enter, enter. So I can get the same matrix as fractions and make sure they're exact values if I ever need to. So anyway, that's how we can do those on here. Let me know if we have questions on that, and I can certainly help, but that's it for lesson 2.